Now we come to a concept called the null space of a matrix. But again, let's just take it step by step. Null space, it sounds like some, like spaceship or something. Let's just take it one step at a time. All these things have fancy sounding words and they sound, sometimes they sound worse than they really are. But let's just see what it is. We learned that if you have a system of linear equations, you could represent that system as a matrix multiplication, where A is the matrix of the coefficients, and X is the matrix of the variables, and the B would be the matrix of the constants, but in this case, all the constants of 0. So it's a homogeneous system of equations. And turns out that if you look at if you consider all the solution set, meaning not just one solution, but all the solutions. Now, there may only be one solution, or there may be many solutions, but whatever that is, whatever the solutions are, if you look at all the solutions, that turns out to be a vector space, a subspace of Rn, meaning because there are Rn in that there are n variables. There are not necessarily R equations. There are M equations, Mike equations, and N November variables. So here's our theorem. If A is an n by n matrix, then the set of all solutions of the homogeneous system of linear equations AX equals 0 is a subspace of Rn, and that subspace is called the null space. And the dimension of that subspace is called the nullity of A. So the nullity of A means the dimensions of the null space of A, and the null space of A is the subspace of Rn, which consists of all these solutions to this homogeneous system of equations. Sometimes they refer to this as the solution space for the system AX equals 0. Just saying, in case you ever see that term, solution space. Anyway, let's go prove this. It's actually not hard to prove. We basically want to prove that all we want to do is prove is that the solution set, the set of all solutions, is closed. So if x1 is a solution, meaning ax1 equals 0. So if I plug in, so x1 is a bunch of values. It might be 3, 7, 9. X2 is a bunch of different variables, the bunch of different solution, -2, 9, 15, whatever. So if I plug in x1 and into this equation, I get 0. If I plug in x2 into that equation, I get 0. Well, if I add the two, let's say I add both sides, ax1 plus ax2 is, in other words, I'm looking now at x1 plus x2. See, x1 is a solution, x2 is a solution. What about this? What about if I add x1 plus x2? Well, I can distribute that. That becomes, because of the linearity, and that becomes ax1 plus ax2. But ax1 is 0, ax2 is 0, 0. Meaning to tell me that if x1 is a solution of the system and x2 is a solution of the homogeneous system, then the sum x1 plus x2 is going to be by definition here, is going to be a solution of the homogeneous system. And similarly, if I take a solution and I multiply it by a constant, so I'm looking at cx1. Well, cx1, I could remember, again, with the linearity and all that, we can, or not even forget linearity. We can pull the. We learned that we're allowed to pull a constant out of a matrix product. So this is equal to c times ax1, but ax1 is just 0. That's the given, and it all equals 0. So if x1 and x2 are both solutions of the homogeneous system, then x1 plus x2 is a solution, and c, a scalar, times x1 is a solution. Hence, the solution set is closed under addition and scalar multiplication, and we learned that that's the test for a subspace. If something is if you have a subset of a vector space that's closed in this way, then it is a subspace. So let's look at an actual example. So we have a matrix here. This is a 3x4 matrix right here. And we want to find the null space. Now, let's just look at it before I even start looking at the solution here. Let's just look at I just want to focus on actually I'm covering stuff up because I just want to focus on the matrix itself. Now, if this is a matrix which is which is going to represent a system of equations. How many equations are there and how many variables are there? Well, this represents a system with 3 equations, and that's based on the 3 rows, and 4 variables, and that's based on the 4 columns. And I would multiply that by x1 like that, and I would give me the big zero vector. In fact, let us. This is going to be a solution. This is going to be a set of simultaneous equations, homogeneous system. And what it's going to actually look like, if I write this in regular way, you write this out in high school or something, it will look like this. This is the matrix A that we were just looking at in print. These are the variables. What you would call X, Y, Z, W, but we're calling X1, X2, X3, XY. These are variables. And here's the solution set. So basically, this means AX1 plus 2. This means x1 plus 2x2 minus 2x3 plus x4 equals 0, and then 3x1, because that's how we do matrix multiplication, and this one equals 0, and then this guy is going to equal 0. Now let's go back to where we are, and let's look at the solution now. Now, so we have a system. Here's the coefficient matrix, and I'm going to put that into reduced row echelon form. So I get 1, 2, 0, 3, 0, 0, 1, 1. And now this system is going to. This means that the bottom row is all zeros. So that means I've basically reduced the system into 2 equations with 2 equations only with these same 4 variables. Now, the best way to make, so we're going to need parameters. And the way to make parameters is we take x2 and x4 to be the free variables, because usually the lead variable, you could really technically make any variable be the free variable, but it's easier if you do not make the lead variable, but make one of the non-lead variables. So in this case, we're going to use x2 be a parameter, and x4 is going to be a parameter. And that means that if I let x4 equal t, if x4 equals t, then x3 is going to be negative t. And here, once x4 is t, 3x4 is 3t, which I bring over to the other side. And I have to let x2 I have to come up with a new parameter for that. We'll call that s. So x2 is going to be s. So now x1 is going to be negative 2s because I'm bringing this over to the other side, and negative 3 because I brought that over to the other side. So now we have our parameters. We have our parameters s and t. X1 is negative 2s minus 3t. X2 is s. X3 is negative t. And x4 is t. And this gives us the solution set now is going to be all these variables, which boil down to this. All I'm doing is taking this line here and just putting it into that matrix and separating it out with I'm separating the s's from the t's. So I get s times this vector plus t times that vector, which means these 2 vectors here, which I'm writing over here, are the basis for the null space of A. And that is how we do it. So obviously the null space here is the basis of the null space is these 2 vectors, which means that the nullity equals 2. The nullity, which is the dimension of the null space, is 2. And notice that the original matrix had 4 columns. The rank of the matrix was 2, and the dimension of the null space, aka nullity, is also 2. Now, some of you may have learned in a previous math class that 2 plus 2 equals 4. coincidence, or is it always that way? There is four, the number of columns, which was 4 in our case, in our example, was 2 plus 2. Well, actually, this makes perfect sense, because if you remember, when we got the rank, we put the matrix into a reduced row echelon form, or even just, yeah. So the columns that have leading ones is going to give us the rank, and the columns that don't have leading ones is going to give us the nullity. So every column, either every column is either going to have a leading one or not have a leading one. So between all of that, you get all the columns. What is it? This one eats no fat, that one eats no lean, and so between the both of them, they look the planet clean. And there's a famous drawing with that. And this is the next theorem is just going to say that officially that if A is a m by n matrix of rank R, then the dimension of the solution space of AX equals 0 is n minus R. In other words, n, which is the number of columns, it's an n by n matrix, so there are n columns. The number of columns is equal to the rank plus the nullity. Now, they have a whole big fancy proof here, but it really all boils down to the argument that we just made a minute ago, that every column either contains a leading one or it doesn't contain a leading one. Well, the ones that do contain leading ones, that's the rank. The ones that don't contain leading ones, that's the nullity. That's why it all works out. Also notice here, it says the word solution space. The solution space of AX equals 0, another way of saying that is the null space of AX equals 0. And instead of saying dimension, instead of saying dimension of the solution space of AX equals 0, another way of saying that is the nullity of A. So we're using a lot of, I think the textbook was using a lot of different words to say the same thing. And I believe it's because the textbook wants you to be familiar with all these different ways of saying it. Because you may, when you read, that's at least my opinion, because when you see a different textbook, if our textbook says null space and a different textbook says solution space of AX equals 0, our book says dimension, the other book says nullity. It's good to, even though a lot of terms, I don't like throwing lots of terms at you because it just makes it more confusing. But on the other hand, it's good to know some of these terms in case a different book will say it a different way. Anyway, moving on. Let's find the rank and the nullity and the basis for the column space of this matrix. So we want to find all these things. So we're looking at the column vectors now. We're going to call them A1, A2, A3, A4, A5, 5 columns, and we want to find the rank and the nullity and the basis of the column space. So the first thing we do with the first thing we do is take this matrix and do elementary row operations to put it into reduced row echelon form, and we get this matrix, our original matrix, becomes this guy, and I'll let you work out all the steps by hand to get to this. Now, notice I highlighted 3 ones. Those are all the leading ones. So the columns that contain those leading ones, well, anyway, I'm sorry. Since there are 3 leading ones, that means that the rank of A is 3. In fact, these 3 rows would be a basis for the row space, and not these 3 columns that we're looking at, but the corresponding columns of the original matrix, A1, A2, and A4. Furthermore, we see that there are now 2 columns left over which do not have leading ones. Those 2 columns would represent the nullity, and that would help us. Excuse me. That would. I'm getting ahead of myself. Anyway, here we have 2 columns that do not have leading ones. So those 2 columns which do not have leading ones, that would correspond. That would mean that the nullity is 2. And of course, if you can't count up to 2, you can count 5 minus 3, whichever calculation is easier for you. but the number of columns minus the rank is the nullity, and that corresponds to the two columns that are left over that don't have leading ones in them. And now, as I said before, the first, second, and the fourth are linearly independent columns. So that means not that these guys are going to be, but the corresponding. So the 1, 0, -2, that's one vector. The where are we here? The 0, -1, -1, 3, and the 1, 1, 1, -1, 0, 1, 1, -1, 0. Those three column vectors will be the basis for the column space of A. And that's it for this video. The next, again, I'm breaking up the section. This section has a lot of stuff, so I'm going to break it up into multiple parts. The next part is going to be dealing with non-homogeneous linear systems. So that's it for now, and I'll see you at the next video.